this video, we're going to look at sample exercise 1, and it asks us to determine how many protons, neutrons, and electrons are in a specific atom here, designated as barium-138. So if you recall, when we talked about the elemental symbol and that's beryllium, and the notation used, so we have Ba, that's our chemical symbol for barium. And then when we write 138 here, this means that this is the mass number, and this is going to be the sum of both protons and neutrons. But if we're asked to find the number of protons, we can simply go to the periodic table. So I'm going to try to journey there. So we see that we have barium down here, and the number 56 indicates the number of protons in barium. So if we go back to our worksheet that we were previously working on, we can see that if we have 56 protons, we can subtract that from 138, since that's our mass number. Minus 56 number of protons, and that will give us the number of neutrons. So if we do 138 minus 56, that gives us 82 neutrons. So now we have all of the subatomic particles for barium-138. So if we made a summary, we would say protons. We got that from the periodic table. There's 56. Neutrons, we subtracted 138 minus 56 to find that there's 82. And then the number of electrons, that will always be equal to the number of protons in a neutral compound. So for part A, we have 56 protons, 56 electrons, and then we have 82 neutrons. So let's take a look at part B here, and we're going to do the same thing. We're going to check out phosphorus 31 now. So a different element, a different specific isotope. So if we were to write this in a different way, it would look like this, that 31 is our mass number. And when we go to the periodic table, we would see that phosphorus is element number 15. So that would be the atomic number here. So to find out protons, that's the atomic number. We find that on the periodic table. Neutrons would be the mass number. So 31 minus 15 will give us 16 neutrons. And then since there's no charge with this specific isotope, we assume that we also have 15 electrons. Let's take a look at sample exercise 2 now, where we're asked about, or to give rather, the chemical symbol for an atom that contains 82 protons, 82 electrons, and then 126 neutrons. So this here will tell us what element we're talking about. So again, if we go to the periodic table and we look for element 82, we would find that to be lead. So we go back to our worksheet here, and we know that we have an isotope of lead. So we're going to put Pb for lead. We don't need to write the atomic number, it's assumed. And now if we add together the protons and neutrons, we would see that we have 208. That's going to be our mass number, and we would write that up here. So if we wrote out the number of protons, it would look like this. If we write the mass number and protons, we have this chemical symbol here. We can also write the isotopic form like this, lead 208. So this is the chemical symbol for an atom with 82 protons, 82 electrons, and 126 neutrons. So there is a device that can be used to determine what isotopes are present, and we can see the percent abundance when we have a certain sample of an element and separate it by the atomic weights of the different isotopes. So if you recall, an isotope has a varying number of neutrons for different elements. And this device is called a mass spectrometer. So it separates different isotopes based on mass. So we can see here that this positively charged chlorine 37 reaches a detector shortly after the positively charged chlorine 35 isotope here. So the lighter elements, the lighter isotopes would reach that detector first, and that's how we can calculate or figure out what percentage of different isotopes we have in a sample. And just to review, when we talk about average mass, it is always going to be the mass of the different isotopes based on their percent abundance. And the unit that we commonly use here is called the atomic mass unit. It's abbreviated AMU. And there is a equivalency here that we have exactly 12 atomic mass units in one atom of carbon 12. So if we break down carbon 12, we should have 6 protons and 6 neutrons. And that's where that number 12 comes from, in carbon 12. There's also another equivalency shown down here that we may use a little less often, where we relate the mass that's given in one atomic mass unit to 1.66054 to the negative 24th grams. So we can see where this equivalency is important here, where we have that 1 gram is equal to exactly Avogadro's number, 6.022, the 23rd atomic mass units. So these relationships may come up a little later on. Let's look at this last sample exercise here from this section, sample exercise 3. And we're told that chlorine has 2 naturally occurring isotopes. There may be more, but these are the main isotopes. And this first chlorine 35, we call it, has an atomic mass of 34.969, and its percent abundance is 75.78. Then we have our second percent abundance here, 24.22. Notice if you add them together, we get 100%. And then that second isotope, the heavier one, the chlorine 37, is 36.966 AMU. So if we wanted to calculate the atomic weight of chlorine, what we might see on the periodic table, we would take the percent abundance, we can convert that to a decimal place like so. So this is for that chlorine 35, and then we'll multiply by the atomic mass in AMU. And then we'll add that that product to the product of the percentage of our heavier isotope in decimal form, 0.2422, and then we multiply that by the atomic mass of the heavier isotope, 36.966. And now when we multiply the percent abundance times the atomic mass and then add that to the other isotope here, we would find with rounding, our sum of our products would be 35.45 AMU. And then if you check on the periodic table, which we can do real quick, and then you find chlorine over here, you can see the atomic mass would be, if they gave us the atomic mass here, it would be the same 35.45.